Today we'll be investigating the universal gas law by looking at Gay-Lussac's law in action. For this experiment, you're going to need some water, a plate with a lip, a lighter or matches, something to stir with, a birthday candle, a small glass jar or bottle, and some food coloring. And remember, with food coloring, it stains, so put on your lab coat and let's get started. First, you're going to add a few drops of food coloring into your water and give it a quick stir. Next, hold your candle over the center of your plate and carefully light the base of it, allowing a few drops of wax to fall on the plate. Move quickly and stick the base of the candle into the puddle of wax and hold it there for a few seconds until the wax is allowed to harden. When you're done, it should look a little something like this. The next step is to slowly pour your water into your plate to avoid splashing. I filled mine up to about the inner brim of the plate, but you don't have to be very precise. Next, I'm going to use my lighter to light my candle, and then I'm going to carefully place my glass jar over the lit candle and observe what happens. We can see that after just a moment, the candle flame goes out and water is rapidly sucked into the jar. Let's look at it again in slow-mo. As the flame dwindles, water is slowly pulled up into the jar, but when it goes out, the water is sucked in rapidly. Now it's time to figure out what's going on here. This diagram represents our setup, and these blue dots represent the O2 molecules that make up part of the air surrounding the candle. We added the water, which is represented by the red color, and then we also lit our candle. When we light the candle, we kickstart a combustion reaction, where the hydrocarbons from the candle wax and the oxygen in the air react with each other to form products such as carbon dioxide and water vapor. The shift from reactants to products is represented by replacing the blue dots with brown dots, which represent the new molecules of carbon dioxide and water vapor. But many factors change as we place our jar over the candle. First, the heat from the flame excites the air molecules inside of the jar, allowing them to move around faster and bump into each other and the walls of the jar much more often. This increased force on the inside walls of the jar is a manifestation of pressure and the first sign of Gay-Lussac's law in action. As the law states, as our temperature increases, so does our pressure, and it's easier for the air to push down on the water than it is on the rigid walls of the jar, so some water is forced out. Also, there's a pressure differential that aids this because the outside air exerts less force on the jar than the inside air does. As the candle continues to burn inside of the jar, the flame begins to deplete all of the available oxygen. When there's not enough fuel left to keep the flame burning, it dwindles before it eventually goes out altogether. When this happens, we are able to see another example of how temperature and pressure are directly related to each other. Without the heat of the flame, the gas molecules in the jar begin to cool down, and because of that, they slow down. The pressure inside of the jar is now lower than the pressure outside of it because the molecules inside are bumping into each other and the walls at a much lower rate. Suction from the inside, in combination with air pressure on the outside pushing down on the water in the plate, forces the water up into the jar. This is shown by the red arrows. Today, we used an experiment to uphold Gay-Lussac's law, showing that pressure and temperature are in fact directly related, meaning if the pressure increases, the temperature also increases, and if the pressure decreases, so does the temperature. I hope you enjoyed watching this video. Thank you!